Imagine you are a data scientist. You have a data lake containing thousands of tables, IMDb dumps, Wikipedia exports, spreadsheets nobody remembers uploading, and somewhere in that mess lies the answer to your question. The problem? No single table holds it. You would need to stitch many of them together. Today, I want to show you how we taught a machine to perform that stitching automatically. This is our VLDB Journal 2025 paper, Table Integration in Data Lakes Unleashed, joint work with collaborators at our MIT, Wollongong, and the University of Queensland. In one sentence, we take many messy tables from a data lake and merge them into a single clean, comprehensive table. Data lakes are gold mines, yet the tables inside are riddled with duplicates, typos, and conflicts. Combining them unlocks knowledge that no single table can reveal, but doing so today is slow, brittle, and demands substantial labeled training data. Our goal is simple: get from many dirty tables to one trustworthy table with almost no labels. Here is what we are working with. Take two tables, one from IMDb and one from Wikipedia. We assume the schemas are already aligned, and we outer union everything into a single intermediate table. Now look closely. US, and United States all denote the same country, written three different ways. And United States? That is a typo. This kind of noise is pervasive in real data lakes, and it is precisely what trips up existing tools. So why is this hard? And what is our angle on each difficulty? There are three challenges. The first is dirty data typos, missing values, and semantic equivalence all tangled together. Our idea is to treat these as small perturbations of a tuple that should not change its meaning, and to use self-supervised contrastive learning to generate positive training pairs automatically, without any labels. The second challenge is label scarcity. Our idea is to let the data teach itself. SSACL manufactures training pairs directly from the data, while for conflict resolution, we lean on a pre-trained LLM with just a handful of demonstrations. The third challenge is multi-tuple conflicts. Our idea is to relax strict clicks to dense communities using a GNN, and then prompt an LLM with compressed, carefully chosen demonstrations to select the winning value. A single thread ties all three together. Let the data, or the LLMs per training, supply the supervision that labels would normally provide. We tackle the full pipeline with four contributions. First, SSACL, a self-supervised contrastive learner that trains a pairwise matcher without any human labels. Second, community-based set discovery. We reframe the problem as finding dense communities in a graph and show that GNs work best. Third, ICLCR, an in-context learning method that uses a large language model with a handful of carefully chosen demonstrations. And fourth, new public benchmarks. Since nothing suitable existed previously, let me walk you through the pipeline. In stage 1, SSACL generates its own training pairs by perturbing each tuple through data augmentation and adversarial examples. So the model learns to be robust to typos and paraphrases with zero labels. In stage 2, we turn these pairwise judgments into a graph whose edges mean should merge, and then use a GNN to find dense communities, a far more forgiving formulation than strict clicks. In stage 3, ICLCR prompts an LLM with the best demonstration examples, compressed via mutual information so that more can fit into the context window. Look at the bottom of the slide. 3 messy Titanic tuples go in, and 1 clean consolidated tuple comes out. And it works. On pairwise matching, we beat the strongest baseline by 4.2% in F1. On conflict resolution, we are nearly 19% more accurate. But the number I care about most is this. When we strip the labels almost to zero, performance drops by less than 10%. That is the entire promise of this approach: serious accuracy without a serious annotation budget. Here is the takeaway. You can perform real data like integration without paying the label tax. Self-supervision, graph communities, and in-context learning together let the data itself do the teaching. Thank you for watching.